Hi, today I'll be talking about Mantis, a framework for implementing expressive and fine-grained reactive behaviors on top of today's programmable switches. This is a joint work with John Sonchak and Vincent Liu. In today's data center networks, a common task is to react to current network conditions. Examples of this type of behaviors include detecting failures and then rerouting around them, identifying malicious flows, and then filtering based on the security policies, and recognizing load imbalance, and then adjusting the traffic distribution. All of these share the same structure, measuring current network conditions and then updating the network devices' behaviors to match them. In data centers, these reactions need to be fast, often sub-RTT level. Today, there are a few ways to implement these type of reactive behaviors. Traditionally, one could leverage the control plane, for example, SDNs or conventional control loops, which can measure the network and reconfigure it dynamically. These approaches are flexible, but typically they are slow and often orders of magnitude slower to capture the transient network events. The other general approach is to try to directly integrate reactions into the data plane hardware. These are fast, but limited by the current hardware capabilities. Now, you might think programmable switches don't fit into this category because they are reconfigurable. Yet unfortunately, there's still a well-known set of limitations. For example, these constraints include limited operations and branching allowed in actions, disconnect of egress-ingress pipeline, unavailability to manipulate match action table entries from the data plane, and so on. Over the years, previous work has come up several workarounds, but these workarounds have drawbacks. For example, one could leverage recirculation to achieve Turing completeness, but it could significantly degrade the usable throughput of the switch. In the end, these workarounds are non-trivial to design and often consume extensive switch resources, even if they are possible. In this work, we explore the question, can we enable in-network reactions to both capture microseconds level events and provide utmost flexibility for encoding the control logic? Our approach is to push the reaction loop as close to the switch ASIC as possible. Meanwhile, co-design the data plane program for fine-grained malleability and ease of use. Hence, we present Mantis, a framework for encoding usable, fine-grained, and expressive in-network reactions on today's RMT switches. At the center of Mantis is a reaction loop, where the Mantis control plane pulls measurements and updates portions of the data plane at a granularity of tens of microseconds. The reaction logic in the control plane can be any arbitrary C code. Specifying this behavior is the P4R language, a simple extension to P4 that enables users to specify which portions of a P4 program should be malleable and to define the reaction logic. The Mantis compiler then transforms the P4R code into deployable codes, ensuring runtime reconfiguration and serializability of the reaction loop. There are two core abstractions underlying Mantis. The first is malleable entities, which is a set of primitives that are amenable to runtime reconfiguration. The second is reaction, which packages the fine-grained reaction logic into a C-like function. For the rest of the presentation, we'll walk through each component of Mantis by taking a top-down approach. First, I will introduce how to express reactive behaviors with P4R using concrete examples. Second, we'll walk through the code transformation that Mantis compiler takes to enable hitless reconfiguration of the data plane. Then, I will elaborate on how does Mantis isolate concurrent operations, and finally, I will describe the Mantis control plane execution flow. To understand what P4R program look like, let's first start with a simple P4 code snippet. Here's a table and action that based on the destination address assigns the priority level. What if we want to reconfigure this priority based on the queue depth? Now, let's look at how to write the corresponding P4R program. First, we declare a multiple entity, for example, a multiple value, that takes 16-bit value and gets initialized to 1. Next, we replace the constant value with a reference to the defined multiple value. Finally, we define the reaction function that specifies the data plane matrix tuple, the arbitrary C code to compute the control logic on a general-purpose CPU, and the reconfiguration of the malleable entities with a simple syntax. Taken together, this reaction pulls the egress queue depths of the first 10 ports, and based on the maximum observed queue depth, potentially sets a lower priority. The control plane executes the reaction function in a loop. The above is just a simple example. It turns out that besides malleable values, which can take on arbitrary numeric values, one could also dynamically reconfigure other P4 objects such as fields and tables. Meanwhile, besides register arguments, one could also specify other data plane objects such as header or metadata fields, malleable fields, and use them as if they were C variables or arrays. So I just showed you the P4R language that is used to specify the reactive behavior. Now, I'm going to talk about how to translate that into something deployable in RMT switches. I will start by talking about how to translate a reaction with a single operation. In M3, we'll later talk about more complex operations and the concurrency issues that result. One of the primary goals of Mantis transformation from P4R to P4 is to create a P4 program that is dynamically reconfigurable. That is, without interrupting the data plane and losing states, Mantis can update multiple entities at runtime. Again, let's look at this concrete example from the previous code snippet. To accomplish this, first, Mantis replaces multiple value pre-var with a concrete P4 object called P4R meta. Then, instantiates the P4R init table with actions to set its value. The P4R init table is applied at the beginning of each packet processing pipeline. Configuring this way means that by changing a single table entry, specifically of the P4R init table, Mantis can reconfigure all use of a multiple value in the entire pipeline. This is true even if we have multiple multiple entities we'd like to change. Note that this initialization table serves for many purposes in Mantis. For example, configuring indirect metadata for multiple fields, version control bits, and so on. This is just a simple example. Transformation of other multiple entities requires further steps, with more details in the paper. Now we have seen how to translate a simple P4R program without considering the isolation. I'm going to talk about additional set of challenges due to the concurrent execution of packet processing and reactions. To see why concurrency potentially causes issues, consider a reaction function that pulls the source and destination addresses of a packet. A user might reasonably expect that the source and destination addresses in a single iteration of a reaction function will come from the same packet P1. However, without coordination, what could happen is that during the first poll, it gets the value of source from packet thread P1, but then during the second poll, it gets the value of destination for another packet P2. Such non-isolated measurement could break the semantics of the reaction logic. Similar problems arise when updating multiple entities in the same reaction. To address the issue, Mantis provides per pipeline, per reaction serializable isolation between measurements, updates, and packet processing. Note that the isolation I'm talking about here is the isolation of ACID, which is to say that all three types of transactions appear to execute in some sequential order, though in fact they are concurrent. This makes it easier to reason about the reactive behaviors. I will talk about the isolation of measurement and the isolation of updates separately. Let's start with the isolation of measurement. Mantis leverages a simple double buffering approach. That means for every argument, we keep two registered copies. These two copies form a working copy and a checkpoint copy. The working copy is updated on every packet, while the checkpoint copy forms a consistent snapshot of the registers. Which one to use is determined by a special measurement version bit. For example, Originally, the measurement bit is 0, so index 0 of the registers serve as a working copy. When the agent is ready to poll, it flips the measurement bit from 0 to 1, making version 1 the new working copy. From that point, version 0 stops being updated, which means that the control plane can poll them without worrying about the concurrent modifications. For register arguments, the approach is similar. We create a duplicate version of the register with twice the instances. One issue with register array is that at most one element of the register will be updated on a packet thread. That means some of the entries may be stale if they were not updated while they were part of the working copy. To address the issue, the agent associates each entry with a timestamp. The control plane keeps track of the timestamp of every measured entry and only takes the newest entries. By applying the approaches above, the control plane will guarantee that all measurements appear to happen at a single point in time. Mantis can also isolate updates. To do so, Mantis leverages a custom three-phase update mechanism for isolating fast, repeated, partial updates. Here's an example to illustrate the idea. Again, let's assume that VV bit stores at 0. During the prepare phase, Mantis applies an arbitrary number of changes to the shadow copy, that is, entries with VV equals to 1. These entries will not be seen by packet processing, as currently entries with VV equals to 0 serve as a primary copy. Note that only the deltas of the reconfiguration needs to be updated. Entries unaffected are left untouched. Mantis then commits the changes by flipping the VV flag, so now VV equals to 1 serves as a primary copy. Finally, Mantis mirrors the changes to the shadow copy to sustain future repeated updates, and then proceeds to the next round of the reaction loop. Note that the stale VV equals to 0 packets will quickly exit the pipeline, typically in hundreds of nanoseconds. Thus, with this approach, 2 versions are sufficient. Mantis therefore bounds the number of replicas to 2 and can complete the full round of updates with latency proportional to the number of modifications. Finally, let's talk about Mantis control plane agent. The Mantis control plane runs on switch onboard CPUs and interact with the switching ASIC. Modern data center switches already use this CPU for tasks such as routing and configuration. However, these interactions are traditionally assumed to be one-off and asynchronous, that is, on a slow path. Instead, Mantis control plane is reaction-centric, and therefore includes a number of aggressive optimizations for repeated accesses and updates of the arguments and multiple entities. Among others, it splits operations into prologue phase and dialog phase, where the prologue phase precomputes as much as it can. It also leverages memorization and several driver level modifications. These allow the dialog phase to quickly poll data plane registers and react to them in users-defined logic, which is expressed in a Turing-complete language like C. Mantis can therefore execute iterations of the reaction loop at granularities that are on the same order of magnitude as PCI latency of the underlying system. We implemented a Mantis prototype that runs on a Tofino switch. The P4R compiler is FlexPython-based and translates P4R program to multiple P4 code and shared objects, handling argument polling and isolation during the process. The control plane agent is a user space thread that dynamically loads the shared object, which encodes the reaction logic. Because it's a shared object, user could also trigger the redefinition of the reaction logic during runtime without interrupting the ongoing switch operations. The front end is available on this GitHub link. Before talking about the evaluation, let me show the usage of Mantis really quick. This is a simple P4R program. Here we declare the multiple entities and a simple reaction. Running the compilation scripts, we get 2 files. This is the generated multiple P4 code. For example, here's the transformation of multiple entities. This is the generated C file, which will be generated into a shared object later linked to the agent. So using this implementation to evaluate Mantis, we focus on the following set of questions. First, what is the granularity of Mantis reaction time and what is the overhead? Next, what are the reactive behaviors that could be expressed with Mantis? Finally, what is the relation of Mantis to existing data plane and control plane alternatives? We begin by micro-benchmarking the Mantis reaction time with a P4R program that pulls variable sizes of field arguments and register arguments and update variables number of multiple entities. For both polling reaction arguments and updating multiple entities, the latency is on the order of tens of microseconds. This is true even if we're accessing and updating multiple entities. For instance, when updating values and fields, as shown in this purple line, updating multiple instances only require a single table update of the P4R init table until the action parameters become too large for the match table's role. Note that all these latencies are predictable in Mantis, which means that we can create a cost model to infer the total reaction time from the two graphs above. We won't go into details, but we found that for all of the use cases we implemented, the end-to-end reaction time was in the tens of microseconds. We also evaluate the Mantis overhead in terms of CPU resources. By default, Mantis agent uses a dedicated core for each dialog loop. However, the CPU utilization could be throttled in exchange for a reaction time. This graph shows the reaction time of updating a single malleable entity. At 100% core utilization, it can complete the update in 10 microseconds. If we throttle it down to 20% utilization, reaction time goes up to around 50 microseconds. Even at full utilization, Mantis doesn't significantly interfere with legacy switch operations like routing protocol operations and operator management tasks. To verify this, we configure a parallel control plane that continuously updates the table on the switch with a normal thrift interface. This represents some of the worst case scenario. Mantis does slightly slow down its neighbor. However, the median and P99 latency penalty are within 4.64% and 6.45%, respectively. We also evaluate the switch memory overhead, and overall, we find that Mantis can successfully coexist with other control plane and data plane modules. Finally, we implemented several use cases that leverage Mantis reaction abstraction. All of these applications can be formulated as a sub-RTT loop that includes measurement, control logic, and reconfiguration. Here's a non-exhaustive list with more details in the paper. We don't have time to talk about all the applications, so I'm just going to show a piece of one. Specifically, we examine the classical problem of flow size estimation. This task has been implemented in both traditional control planes and programmable data planes. Hence, it provides a useful comparison point for Mantis. In traditional control planes, flow size estimation often uses approach like sFlow, which samples packets and estimates flow sizes stochastically based on the samples. In pure data plane approaches, commonly used techniques include flow caches and sketches. This graph shows the average estimation error versus the flow size. Slower is better. The trace we use is from Cadet ISP backbone and classifies flows by their source addresses. For sFlow, the pure control plane technique, the error is relatively high but stable across the range of flow sizes. The data plane approach have much better accuracy until they go to small flows, where collisions overwhelm the predictions. Mantis, with the same resources, can pull the data plane at 10 microsecond granularity, essentially pulling once every 5 packets. This allows it to outperform sFlow across all sizes. In addition, because Mantis doesn't suffer from hash collisions compared to data plane approaches, it approximates them for large flows and significantly outperforms them for small flows. So to summarize, Mantis introduces fine-grained reaction to network statistics as first-class citizen. Mantis simplifies the process of defining reactions and provides simple to reason about set of reaction abstractions with P4R programming interface. and enables a wide range of sub-RTT reactive behaviors without penalizing the line rate packet processing speed. Thank you so much for your attention.